We often find ourselves in the position of explaining our work to those who view artificial intelligence as a monolith, a singular engine of magic that produces answers from thin air. But for those of us who sit in the architect's chair, we know that the reality is a nested hierarchy of increasing specialization and decreasing transparency. To understand the comparison between artificial intelligence, machine learning, and deep learning, we must first strip away the marketing jargon and look at the fundamental way these systems process information. We begin at the outermost shell, the broad field of artificial intelligence, which is less a specific technology and more a goal. Since the 1950s, the objective has remained constant: to create a machine that can perform a task that, if done by a human, would be considered intelligent. In the early decades, this was achieved through symbolic AI, or what we now affectionately call good old-fashioned AI. This was the era of the expert system, where intelligence was synonymous with logic. As architects, we were essentially translators, taking human knowledge and codifying it into thousands of interconnected if-then statements. The architecture of symbolic AI was transparent and deterministic. If the system reached a conclusion, you could trace the exact logical path through the decision tree to see why. However, this approach hit a wall because it lacked the ability to handle the fuzziness of the real world. A symbolic AI could play a perfect game of chess because chess is a closed system with rigid rules, but it couldn't recognize a handwritten digit because the variations in human handwriting are too numerous to be hard-coded. This limitation birthed the second layer of our hierarchy, machine learning. The pivot from general AI to machine learning represented a fundamental shift from deductive reasoning to inductive reasoning. Instead of giving the computer rules, we began giving it data and asking it to discover the patterns itself. This is where the concept of the model truly begins. In machine learning, we are no longer writing scripts, we are defining objective functions and optimization routines. When we look at the architecture of a standard machine learning system, the most critical component is the feature vector. For a technical audience, this is the point of greatest friction. In classical machine learning, the human remains the primary feature extractor. If you are building a support vector machine or a random forest to predict financial fraud, the machine does not look at the raw data of a transaction. It looks at the features you have engineered for it, the frequency of transactions, the geographic distance between them, the variance from the user's historical mean. This process of feature engineering is where the intelligence actually resides. The machine learning algorithm is simply a statistical engine designed to find the optimal hyperplane or decision boundary in a high-dimensional space defined by those human-selected features. We are essentially mapping our domain expertise into a format the computer can optimize. The mathematical heart of machine learning is the trade-off between bias and variance. We are constantly seeking a model that is complex enough to capture the underlying signal in the data but simple enough to ignore the noise. In architectures like gradient-boosted trees or logistic regression, we have a high degree of control over this. We can prune our trees, we can apply L1 or L2 regularization to penalize overly complex weights, and we can perform cross-validation to ensure our model generalizes to unseen data. This level of control is why machine learning remains the backbone of enterprise technology even in 2026. It is computationally efficient, it runs on standard CPU clusters, and perhaps most importantly, it is interpretable. When a machine learning model makes a prediction, we can look at feature importance scores to see exactly which variables drove the decision. We are still the masters of the data's representation. However, as the volume of data grew and the complexity of the problems shifted from tabular data to unstructured data like images and speech, the manual process of feature engineering became a bottleneck. This brings us to the transition into the innermost core, deep learning. While machine learning algorithms struggle when the number of features becomes too large or when the relationship between those features is highly nonlinear, deep learning thrives. The architectural leap here is the move from shallow, feature-dependent models to deep, hierarchical representations. In deep learning, we stop telling the machine what to look for and start building architectures that allow the machine to figure out what is important on its own. This is the representation learning era, where the raw input, pixels, audio samples, or tokens, is fed directly into the system. In a deep learning architecture, we utilize layers of artificial neurons, each performing a weighted sum of its inputs followed by a nonlinear activation function. The deep learning refers to the stacking of these layers. From a technical perspective, each layer acts as a filter that transforms the data into an increasingly abstract representation. The initial layers might capture low-level gradients or textures, while the deeper layers synthesize those into complex topological features. The magic and the challenge lies in the fact that these features are not human-readable. The machine might decide that a specific arrangement of shadow and contrast is the most predictive feature for identifying a specific sportsman's gait, but that feature exists only as a specific activation pattern across 1,000 hidden units. We have traded our ability to engineer the features for the machine's ability to discover them, and in doing so, we have moved from the transparent world of machine learning into the black box of deep learning. As we move deeper into the inner workings of deep learning, we must discuss the mechanism that makes this automated feature discovery possible: backpropagation. While a machine learning model might find its optimal parameters through a closed-form solution or a relatively simple optimization, a deep learning model requires a continuous, iterative feedback loop. Every time a neural network makes a prediction, it calculates the loss, the difference between its output and the ground truth. It then uses the chain rule of calculus to propagate that error backward through every single connection in the network, slightly adjusting the weights to reduce the error the next time. This process, repeated millions of times across billions of parameters, is what allows a deep learning model to learn the manifold of the data. For the technical architect, this introduces a new set of challenges that don't exist in classical machine learning. We have to worry about vanishing and exploding gradients, where the signal becomes too small or too large as it travels through the layers, effectively halting the learning process. We combat this not through feature engineering, but through architectural innovations, residual connections that allow the signal to skip layers, batch normalization to keep the activations within a stable range, and sophisticated optimizers like Atom or Lion that adapt the learning rate for every individual weight. The complexity has shifted from the data's representation to the network's topology. We are no longer data engineers so much as we are gradient engineers. The primary reason deep learning has eclipsed traditional machine learning in specific domains is its relationship with scale. In classical machine learning, there is a saturation point. Once you have a few thousand high-quality examples, adding more data often yields diminishing returns because the model's capacity is fixed by its simple architecture. Deep learning, however, follows the power laws of scaling. As we increase the number of parameters, the amount of compute, and the volume of data, the performance continues to improve, often exhibiting emergent behaviors that weren't present in smaller versions of the same model. This is why, in 2026, we see models with trillions of parameters. These systems are capable of capturing the subtle nuances of human language or the physics of a moving body in a sports video because they have the room in their architecture to store that complexity. However, this performance comes at a massive cost. Deep learning is orders of magnitude more expensive than machine learning. It requires specialized hardware, GPUs and TPUs, that can perform the trillions of matrix multiplications required for a single pass. It also requires a different approach to data. While machine learning requires clean data, deep learning requires diverse data. Because the model is learning its own features, it is incredibly sensitive to biases in the training set. If a deep learning model used for a sports retrospective only sees footage from sunny days, it may fail to recognize an athlete in the rain, not because it doesn't understand the athlete, but because it has incorporated the sunniness into its internal representation of what a sport looks like. Looking at the comparison through the lens of 2026, we see a fascinating convergence. We are no longer choosing between AI, machine learning, and deep learning as if they were separate tools in a box. Instead, we are building neurosymbolic systems that attempt to combine the best of all three. We use deep learning for the high-level perception, recognizing the sportsman, understanding the audio narration, but we often wrap that in a machine learning or symbolic logic framework to ensure the output is consistent and follows the rules of physics or the facts of history. We might use a transformer-based deep learning model to generate the video frames, but we use a classical machine learning algorithm to handle the temporal smoothing and ensure the motion doesn't jitter. The takeaway is that the best architecture is the one that matches the entropy of your problem. If your data is structured and your rules are clear, The broad tools of AI and machine learning will provide the most robust and cost-effective solution. But if you are trying to bridge the gap between human expression, like audio narration, and visual reality, you must descend into the deep learning core. You must accept the loss of interpretability for the gain of expressive power. The history of our field is a steady march from us telling the computer how to think, to us showing the computer how to learn, to finally building systems that can perceive the world within complexity that mirrors our own. Our role has evolved from being the authors of the rules to being the curators of the experience and the architects of the loss functions that guide these digital minds.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.